Okay, so today we're going to take a look at another application. Um, Less of a machining application and more of a construction application, but there are parallels in the machining world to it. So we're going to take a look at having a wedge. We're going to give this a 3 to 5 aspect ratio on our wedge. And across the bottom here, let's call this a 40 millimeter length. So now, oops, I can get things adjusted here so I can actually see them. What we're going to do is from the bottom right corner here, we're going to extend a line straight up. So yes, that is a right angle there. From the peak, we're going to bring a line coming down, and that line is going to have a 2 to 3 slope on it. And these two lines then are going to be joined together by an arc, the radius of 8 millimeters. So what I'm asking you to find here are two dimensions. X is the distance from the tip of that, from the peak, if you will, to where the curved portion starts. So the length of that straight line or flat surface there. And then Y is going to be the length of this vertical line. Again, from the base until it comes up and hits that arc. So to work on this, there's a lot of different things that have to come into it. But the first thing we usually would see is we have tangents to a circle. For a straight line to flow into an arc, that line has to be tangent to that arc. So that means we can put in a radius here with a right angle there and a right angle here. Now that center of that circle, even though it looks like it's drawn on this line here, is not necessarily on that line. So we have to be careful to note that we cannot make that assumption. In the drawing, it looks like it's there, but it might not be. In fact, let's do this to make it more obvious that it's not. The center of that circle, the circle that would form that arc, is not on that line on the edge of the wedge. The thing I'm going to do, just because it's relatively easy to do, is I'm going to find this overall height of the wedge, because it's a relatively simple process to find it. Our aspect ratio is 5 to 3, which means I can draw a triangle that would look something like this, where this edge is 5 and this edge is 3. And I know that this portion, this right triangle, has to be similar to that. So I need to find one of the dimensions, and I can find the bottom dimension here, assuming this wedge is symmetrical. With 5 to 3 slope on both sides. We can cut that 40 in half to give this piece is 20 millimeters. So then we can find, if I call this H here, 5 over 3, vertical over horizontal, has to equal vertical over horizontal. Well, the vertical there is the H, the horizontal is the 20. So to find H, we cross multiply and divide. 5 times 20 divided by 3 gives us H is 33 and a third, or 33.33. That is important for a few reasons. One is it is going to allow us, it's a total height for us. So now we can break that total height down into pieces that stack up to it so that we can find missing pieces of missing vertical components of that height. So the next thing I want to do is I want to look at that dimension X. The reason I want to look at dimension X is because it has an aspect ratio to it that's going to allow us to find a right angle. I'm going to actually look at this triangle right here. So I'm going to draw it off to the side over here. The hypotenuse of this triangle is X. I know this angle right here. I know that angle because it'll come from this 2 to 3 aspect ratio. 2 would, if I'm looking at that angle, 2 would be the opposite side, and 3 would be the adjacent side. So that angle is just the inverse tangent of the opposite side of 2 over the adjacent side of 3. Second tangent, 2 divided by 3, gives us 33.69 degrees. This point, that's the only dimension we know on that triangle is that angle. Well, we know 2 angles. We know the right angle. And I suppose because of that, we do know that this third angle down here has to be 56.31 degrees. So we know all 3 angles of that triangle. We just don't know any sides quite yet. There, the one thing that we do know about it is we do know that this side is less than 20 because it has to be less than half of our 40 millimeters down here. The reason I wanted to find that triangle so bad, even though we can't go any further with it, we're going to have to come back to it, is because that triangle helps me to define this triangle down here. That triangle down there, I'm going to draw it right here, has a few features that we know. First of all, we have the right triangle that's given. It's given because I drew this in as a vertical dimension here. And of course, the other one was already horizontal. So I'm using that idea. We haven't used that for a few days of vertical and horizontal dimensions coming together to form a right angle for us. The other thing we have, this hypotenuse of that is the radius of our circle here that has to be 8 millimeters. And next, we know that this is a right angle here, so that's 90 degrees. So we have a case here where it's not 2 angles, but 3 angles that come together to be supplementary. These 3 angles here have to add to 180. That makes this angle right here 33.69 degrees. Now that we have that angle is 33.69 degrees, we can find both this piece here, which I'll call A, and this piece down here that I'll call B. Find A first. Well, according to my angle up there, the 33.69, A would be the adjacent side. 8 would be the hypotenuse. I have to use the 8 because that's the only side that I know. Adjacent and hypotenuse makes up a cosine. So cosine of 33.69 degrees equals the adjacent side of A over the hypotenuse of 8. Since we are looking for a missing side, we put the trig function over 1 to make a proportion, and we'll solve it by cross multiplying and dividing. So we have the cosine 33.69 degrees times 8 divided by 1, giving us 6.656 millimeters for A. So that is that vertical dimension. That would be this piece right here. Now we can find B. Now we could find B a couple of ways. We could use A squared plus B squared equals C squared. But I'm just going to go ahead and keep using trig so that I don't have to reuse this number here, since I know that that number is rounded. You know, it's really 6.6564. Rather than reuse that rounded number, we're going to start from fresh numbers. So B over here, from our angle of 33.69 degrees, B would be the opposite side. Opposite hypotenuse is a sine. So we have the sine of 33.69 degrees equals that opposite side of B over hypotenuse of 8. So again, I'm looking for a missing side. I'll make it in a proportion by putting the trig function over 1, and I will cross multiply and divide. The sine of 33.69 times 8 divided by 1 gives us 4.438. Now, why that bottom piece, B, is important is because I can come up here. If this is 4.438, this piece here has to be 3.562. Why? Well, because that is a radius of our 8 millimeter circle. So that has to be 8 millimeters. So we can subtract the 4.38 from 8 millimeters to get that distance of 3.562. Well, once again, why is that dimension important to us? Well, because it takes us back up to this triangle. From here out to the edge is 3.562. The whole thing has to be 20 millimeters, half of the 40. So this piece up here is 20 minus 3.562, otherwise known as 16.438 millimeters. Now that I have that dimension, I can find this dimension here. Because I'll use my 33.68 again. I'll call this dimension over here D. D would be the opposite side. The 16.438 would be the adjacent side. We are looking at a tangent. Tangent of 33.69 degrees equals opposite side of D over the adjacent side of 16.438. Once again, we put that over 1, make it a proportion, and we will cross multiply and divide. Tangent 33.69 degrees times 16.438 divided by 1. You know, it's 10.959. So this dimension here is 10.959 millimeters. Now we can find X. X is just right here, the hypotenuse of that triangle. We could do A squared plus B squared equals C squared, but that's going to require us to use two dimensions that are both rounded. So let's just do, using that 16.438 and our 33.69, let's just do the cosine. the cosine of 33.69 degrees equals, the adjacent side is 16.438 over the hypotenuse, which is x. Again, we're looking for a missing side, so I'll put my trig function over 1 to make it a proportion so that we can cross, multiply, and divide. So here it's 1 times the 16.438, which is 16.438, divided by the cosine of 33.69 degrees. Yes, 19.756. So x, right here, 19.756 millimeters. There's one of our two dimensions that we needed to find. I'm going to label that large down there so we don't lose track of it. So the only thing left for us to find, or that we're supposed to find or asked to find, is y here. Well, we already have all of those pieces. The total height is 33.33. We have the rise from the top triangle up there, this one here. We've got that rise of 10.959. And we have this rise here of 6.656. I is just from there down to the bottom. So that would be this dimension here would be y. So to find y is just our 33.33333. That was 33 and a third, really, remember. And I put a third 3 in there. If you don't put it in your calculator, your answer will be slightly different. It's all just round off errors here. I'm putting in the third 3 just to stay significant to 3 decimal places. So minus 10.959 minus 6.656, we get 15.718 millimeters for y. So here's the two answers we were looking for. A couple of things in this problem. A couple of reasons why I like this problem, even though it's less of a machining problem, more of a construction-based problem with the intersecting roof planes, is because there's a lot of good mathematical practices here, or a good opportunities to learn from mathematical practices here. First is the way we had no choice but to jump around. What do I mean by that? Well, we found this triangle up here first, but we were only able to find certain pieces of it. So we were able to find angles of that triangle. Then we had to set it aside and leave it, using those angles that we found to work on another piece. Then we completely solved that piece. Then we went back up to where we were doing what we were doing with that first triangle. I didn't do the greatest job of keeping things neat and organized here, but this is the type of problem where it is essential that you have some sort of organization, because as we saw, we worked on this for a while. We had to set it aside using that information to do other stuff and then come back to it later to find the rest of it. If you're not organized, you're not going to be able to find where to go back to get to those pieces. Now, more of a problem solving and life lesson there than it is a math lesson. But it's very important as we hit these more complex problems that you are able to do that. Now, the other thing here is this problem has all sorts of different directions you could have gone with it. You might have would have been very tempted to start with this triangle down here for y. So that's a right angle, and this side here is y. And it looks like we don't know anything else about it, but we actually do. Because this base of the wedge intersects that, we know that that's an overall right angle. We actually could have found this angle here because we know that sloped surface was a 5-to-3 slope. We could have found 5-to-3. We could have found this angle here as the inverse tangent of 5/3, opposite over adjacent. Giving us an angle of 59.04 degrees here, which gives us an angle here of 30.96 degrees. At that point, however, we could have found, of course, this angle as 59.04. So we have all three angles of that triangle, and that's it. We don't have any other information going with it. The temptation that many people would fall into here that would be absolutely incorrect would be to try to call this 8 millimeters here. That's why I made such a huge deal at the beginning. The center of this triangle is not on this edge of the wedge. The center of that arc of the circle, I should say. Because for this to be 8 millimeters, the only way that would be possible is if the center of that arc was exactly on the edge of the triangle. It's not. It might be, but we don't know that it's there. In fact, let's check. If y is 15.718 millimeters, we know that this is 30.96. That opposite side, we'll use the tangent of 30.96 degrees, equals that opposite side over 15.718. Put that over 1 and cross multiply and divide. And we get 9.429. It is definitely not 8 millimeters. So that's telling us that the center of that circle was actually somewhere in here. It was outside of the wedge. Definitely not on the wedge. That actual dimension was 9.429. So the danger there is making assumptions that look reasonable. When we first drew this out, it looked reasonable to assume that center of the circle creating that arc was on the edge of the wedge. That's an awkward rhyming scheme there, huh? It's on the edge of that sloped surface, but it really isn't. And if you make that assumption, you get an answer that looks very reasonable, but is very, very incorrect. In fact, once you have found the angles of that wedge, there's really not much else you can use it for, because those angles do not relate to the angles of the arc of that sector of that circle at all. It's the angles up top here in this triangle that allow us to relate to the circle because of that right angle between the radius and that piece. Okay, I have babbled on long enough. Let me make sure I know what is out there in Blackboard for you guys for today. There is not a new quiz today. Won't be a quiz until early next week. So all that is out there is homework. There is a worksheet that is labeled April 15th for you. So I will give you guys the rest of the time, because these are more difficult problems and take a little time to put together. The second problem is one that we did a few days ago. I'll leave it out there to see if you can remember how to do it. If not, we'll go over it again on Monday. We're kind of at that point in the course. We have a few extra days at the end of the semester here, so if any of this stuff gives you a lot of trouble, please don't be afraid to let me know, and I will take an extra day to go over any of these examples. Like I said, we've got about 3 hours of class left over right now planning out the semester, so if we have to push stuff back to go over things again, we don't have an issue with that at all. So with that, I will shut off the recording and let you guys get to work.